Welcome to my talk about our research on IJON, an approach to explore deep state spaces with fuzzers. Academia mostly focuses on fuzzing as a fully automated process, and I think there is a merit to that point of view, as it is easy to use fuzzers that follow this approach, as they are easy to apply to a wide range of test scenarios, and specifically security testing. And I really believe this is the major reason behind the large success story behind AFL and libfuzzer. However, for a security professional, it's often very helpful to have a more fine-grained control of the internals and the behavior of a fuzzer. And it's reasonable to expect a security professional to have a fundamental understanding of how fuzzers work. In this paper, we look into how an expert human with a reasonable understanding of fuzzers and a limited understanding of the target application can help and guide the fuzzer. As a consequence, I think we come up with some pretty interesting ideas on how to develop further fully automatic fuzzers. So let's do a quick recap on how modern fuzzers actually work. In a modern fuzzer, we typically start with a target application and a given set of seed inputs. In many cases, we can use an empty seed input or a single seed input containing only A's. From this seed input, the fuzzer generates mutated versions, observes the test coverage generated by these mutations, and if any new coverage was found, it stores the input in the queue of inputs considered for further testing. If a mutation does not trigger new code coverage, it is discarded immediately. As we mutate inputs that were previously found by mutations of other inputs, we can incrementally learn a set of test cases that generate good test coverage. Looking at this from a high-level point of view, we can see that the fuzzer classifies inputs as equivalent if they cause the same coverage, and thus the fuzzer partitions the space of all inputs into large equivalence classes. If we start from a given set of seed inputs, then the equivalence class of all of those seed inputs are immediately marked as boring. As we keep mutating the seeds in the input queue, we will mostly hit other inputs that are within the boring regions of the input space. However, every once in a while, the fuzzer is able to uncover an input that actually triggers new coverage and thus belongs into a new equivalent class. This input is stored in the queue for further processing. As we keep iterating this process, the fuzzer finds more and more interesting inputs and hopefully is able to find inputs that test most features of the application. If the interesting areas in the input space are close together with respect to the mutations and small enough such that inputs in one area are likely to create mutations in another area, then the fuzzer usually works very well. However, due to general undecidability, this is not always the case. In many cases, some of the equivalence classes are too large for the fuzzer to explore sufficiently. In such a case, the mutation engine is not able to generate mutations that reach far enough. While some approaches focus on creating larger mutations that still maintain their ability to mostly trigger interesting inputs, in this paper we are concerned with creating better feedback. The first and obvious approach for this is to split large equivalence classes into multiple smaller ones that the fuzzer can effectively explore. One example for such a technique is AFL-Lafintel, which splits multi-byte compares into smaller ones where each individual solved byte of the multi-byte compare immediately causes new coverage. The key idea behind this talk is to combine the coverage feedback that is used by most modern fuzzers with selective value feedback, where the user selectively annotates data of the state space that should also be considered as part of the feedback function. Thus, we're able to provide very fine-grained feedback on individual values without overwhelming the fuzzer with all the noise of other values in the state space. As a consequence, we're able to use feedback functions that are much more detailed than it would be possible if we were to apply the same feedback function to the whole program at once. Consider the simple maze game that is commonly used to demonstrate CLE's ability to uncover test cases. The player has to use W, S, A, and D keys to navigate the maze. In the original version, the player is not allowed to visit positions that were previously visited. To increase difficulty, we created a second version of the maze where the player is free to move to old board positions. In this case, neither current fuzzers nor CLE are able to solve the maze game in reasonable amounts of time. This is due to the fact that the set of states that the application can be in after n key presses grows exponentially. At the same time, code coverage ceases to be useful after each key has been pressed once. A human analyst understands intuitively that the values that we care about are only the x and y coordinates. Using this insight, a human user is able to provide a simple annotation that tells the fuzzer to regard any new combination of x and y coordinates as similar to new coverage. IJON allows the user to provide such an annotation with a small piece of inline code. Using IJON and that one-line annotation, AFL now is able to solve the maze in a matter of seconds. While this is an encouraging result, obviously we care more about finding bugs than we care about solving maze games. So let's have a look how we can apply the same ideas to real-world targets. The reason that the maze game is complicated to both fuzzers and symbolic executors is due to the fact that the implicit state machine of the maze game itself is obfuscated by a much larger implementation as a C or x86 program. Similar situations occur in many real-world programs. Consider, for example, a simple FTP-like protocol. Here, a sequence of messages have to be parsed and consumed for the target application to be in an interesting state. A user that read the RFC is easily able to deduce that most of the code coverage happening before the first hello message is received is in some sense equivalent. Similarly, code coverage that happens between hello and the first login also seems to belong to a given state. And lastly, after we successfully authenticated, the rest of the code coverage also belongs to an individual state that is unlike previous messages. This can affect how we explore message parsing. Consider the example of different directions in the maze game. Similar situations occur if the program parses different message types. Using similar annotations, we can help the fuzzer understanding programs without providing a full specification of the input. Let's have a look at a concrete example. In this case, we're looking at libpng and a specific bug that was previously found by another fuzzer using a precise specification of the PNG file format. A PNG file consists of a general PNG header and then a list of chunks. Each chunk consists of a length field, a type, and then some data. libpng contains a loop that basically iterates over all chunk headers and handles each individual chunk. To help the fuzzer explore structurally different PNG files, we introduce a small annotation that keeps track of the last 4 different chunk headers that we observed. Every time we observe a new succession of valid chunks, we introduce additional artificial coverage that helps the fuzzer to store many different and valid PNG files in its own queue. As a consequence, the fuzzer is able to explore a much more diverse set of inputs. To uncover the bug, the fuzzer has to have a specific sequence of chunks, including 2 different versions of the same chunk. AFL is unlikely to store such an input as it does not introduce interesting coverage over other inputs with similar but different chunk structure. Using a specification, a fuzzer is able to generate such inputs more easily. However, to generate a specification, the analyst needs to have a precise understanding of the input structure of the target application. Using our approach, we can apply similar annotations in a wide variety of settings with little understanding of the precise input format. While introducing fake coverage based on existing data is one way to guide the fuzzing process, there's other ways to achieve the same goal. In many cases, where the input equivalence class is too large, we're actually able to identify a primary direction that tells us that we're getting closer to a novel area in the input space. Consider this example where the fuzzer is supposed to solve the factorization problem for a small integer. No matter the input, if it does not solve the factorization problem, it will be immediately discarded. By providing a small annotation that states that we wish to minimize the difference between the left-hand side and the right-hand side of the equation, we can drastically change the feedback landscape. Using this additional annotation, the fuzzer is now able to systematically explore the input space to find a solution. To give a more visual example for this behavior, we combined the maximization feedback with Super Mario Bros. By adding a small annotation that states that we wish to maximize the player's x coordinates, we turn AFL into a surprisingly competent Super Mario Bros. Speedrunning bot. In these pictures you can see AFL and AFL with that one-line annotation playing Super Mario Bros. In different levels. As you can see, using the annotation, AFL and IJON are able to finish the level, while AFL without the annotation mostly explores different jumps in the first part of the level. However, it is quite surprising how well AFL actually performs as a bot in Super Mario Bros., given that it was designed to fuzz binary input formats and not play games. And in fact, AFL is actually able to solve some of the easier levels even without IJON annotation. Observing AFL using our IJON annotation play Super Mario Bros. Also displays some of the more interesting problem cases. For example, this level is much longer than most other levels, and as we can see, even with the annotation, IJON fails to solve the level. This is due to the fact that in interactive applications such as Super Mario, and many applications more related to the field of IT security such as web servers, code that requires a long-running input actually is at a cubic disadvantage. First of all, the queue grows, and the most promising input will be scheduled less and less. Secondly, the most promising input is also becoming longer and longer. That means the most promising bytes are mutated less and less. And lastly, each individual execution gets drastically slower. Solving these issues would help fuzzing to move from working mostly for binary blobs to much more complex interactive applications. While playing Super Mario is of course a rather entertaining example, we're after all working in IT security, so we're more concerned with IT security related issues. So let's have a look at a way that we can use this annotation to explore programs' behavior and to confirm suspicions that we already have. During the evaluation of this paper, we looked at some programs that were recently fuzzed in other papers. And in one particular example, we got the impression that there might be an integer overflow in this call to malloc. Using a single one-line annotation, we can tell IJON to try to cause this specific overflow. And indeed, this allows us to uncover that the given code is vulnerable to an integer overflow that leads to a zero-sized allocation within a few seconds. We also investigated the well-known CGC dataset containing 226 challenges, of which, with current state-of-the-art fuzzers, 62 remain undefeated. We manually inspected 30 of those challenges. As we used the x86 port by a trail of bits, roughly 1/3 of the challenges were broken, that is, they didn't crash even with the provided proof of vulnerabilities. We could find simple IJON annotations for another third of the examples. Here some interesting patterns emerged. For example, some of these problems require checksums or even challenge-response mechanisms. We removed the checks during fuzzing, and then used AFL's crash exploration mode and one of the IJON max annotations to solve the checksums of the crashing inputs found. This approach closely mirrors tfuzz, but it entirely avoids using symbolic execution, as all those cases could be solved by much simpler annotations using the maximization primitive. Also, a surprisingly large number of challenges required only to maximize a single pointer or loop counter, suggesting that current fuzzers are not particularly good at exploring this kind of code. Lastly, a surprising amount of challenges were solved by fixing simple variants of string compare, suggesting that magic bytes are still not entirely solved. Finally, about 1/3 of the remaining challenges could not be solved even with IJON annotations. The most common causes for this were typically that the challenges expected very large inputs. For example, some challenges expected a game to be played for many 10,000s of rounds. Additionally, some of the challenges would in theory be solvable by IJON annotations. However, the annotations required would be so complex that it would be very hard to come up with the annotation without prior knowledge of the bug. Based on these observations, we think